seen in other sessions. I guess don't be disappointed that there is only 9 participants so far. Mostly a few minutes after the start of the session, few people will join, and also
recording in progress.
And also we have mostly many people who watch the session on YouTube because they have better access to that. I see that all speakers of the session are already here. I see Jakob, Tatiana, and both Alexandros. Hi, Jakob. Nice to see you again. It's pretty easy. The speakers just share their screen. There is no, I don't have to give permission. You have the permission. So I guess you could start to share your screen, Jakob, and okay. We'll start in time at 2 p.m. of my time. So maybe we wait until we, so we don't start early, so to give people the chance to join. All right, it's 2 o'clock. Welcome everybody to seminar 2, to this noon or afternoon session. Unfortunately, Charles Mukamel informed me that he's not able to chair the session. Those of you who are going to watch the talks afterwards, the plenary talks, we'll see him. Maybe he's doing last-minute preparation, whatever. I'm happy to chair this session and welcome you. And it's a pleasure to welcome the first speaker, Jakub Bender from Charles University in Prague, Czech Republic, who together with Zdeněk Mažin worked on polarization-induced molecular photoionization delays and equivalence of rapid and streaking dipole laser coupling, and I'm very much looking forward to your talk.
Thank you very much. I would like to thank the organizers also for the invitation to this talk. It's really something for me. I will tell you what we are up to at Charles University regarding the molecular photoionization. So in our small theory group, we are looking at attoseconds delays, among other things. The central quantity of interest is the photoionization delay, sometimes called Eisenbach-Wigner-Smith or one-photon delay. And it's the effective time of the ejection of the photoelectron relative to the peak of the ionizing laser pulse. This time delay is hidden or contained in the energy dependence of the photoelectron wave function's phase, and as such, it's quite difficult to measure directly. So various methods exist to extract this quantity indirectly. One of them, which I will focus on the most, is the weak field interferometric method of rabbit reconstruction of attosecond beating by interference of two-photon transition, where the sample of molecules is ionized by 2 nearby frequencies, giving or erasing or creating a superposition of 2 different energy states of the photoelectron, and these are then brought back together by suitably tuned infrared field. Alternatively, there is another method, attosecond streaking, with a somewhat stronger infrared field, where the momentum of the photoionized electron bears an imprint of the instantaneous value of the vector potential at the moment of the photonization, and can be used to extract the timing information. Both these methods involve, as I said, some extra field on top of the ionizing field, and as such, the delay that they measure, or that can be extracted from them, may contain some contamination, some additional information, which may also potentially obscure what we are interested in, and it's good to understand it. So in case of Rabbit, the most typical setup, the new information, or the extra delay, is an attosecond delay component that comes from the Coulomb force mediated free transition. When we look at the Rabbit process in the single channel model, and often coupled with a single active electron approximation, we have the following picture. The initial state of the molecule absorbs one of the two components of some highly energetic laser field and creates the molecular ion in some state, and the photoelectron in a superposition of two momentum states. These, again, absorb or emit some low energy photon, and this brings both pathways together so that they interfere, and we can extract the phase information. This two-step process gives a natural splitting of the measurable time delay into the one photon or Eisenbach-Wigner-Smith delay associated with the first ionization or first absorption, and then the continuum delay associated with the stimulated emission or absorption of the second photon. In equations, or symbolically, the Rabbit delay is calculated, or can be calculated, as a difference between phases of the two photon ionization amplitudes, and these can be obtained from the second order perturbation theory, from the initial and final state of the system. And then there are the perturbations, dipole operator, and polarizations of the fields, and the Green's function. The right-hand part can be combined into the intermediate state, and the intermediate state, roughly symbolically, can be written as a product of the one photon ionization amplitude, the final or intermediate molecular ion state, and the photoelectron wave function. The remaining bracket is essentially a radial integral over the coordinates of the photoelectron, and then the two photon matrix element is a product of two terms, one which has the phase that corresponds or contributes then to the Eisenbach-Wigner-Smith delay, and one which gives rise to the continuum delay. If we do the derivation more accurately, there is some partial wave mixing. So we talk instead about the molecular delay, but that changes the situation very in a minor way. The question is, what's the correct multi-channel generalization of this picture? Of course, obviously, we don't need to account for changes in the residual ion in addition to those in the photoelectron itself. And the picture then looks, for example, like this. The molecule is ionized. It ends up in a mixture of states of different molecular residual ions, and the photoelectrons coupled to these states. And then the infrared field mixes and matches all these combined states and creates some other superpositions. It is natural to expect that this will result in some extra additional contribution to the time delay. This is most clearly illustrated in the carbon dioxide, whose states B and C of the cation are spaced or separated by 1.3 electron volts, which is very close to a typically used energy of infrared field, 1.55 electron volts, and also these two states are quite strongly dipole coupled. There is a large transition dipole matrix element between these two states. So this is quite efficient process, the flipping between these two states mediated by the infrared field. And what we see is that the electron, the photoelectron, which leaves after the first ionization the molecule in some states, leaves the molecule still subject to the infrared field, and there is some dynamics in the residual ion which can eventually flip these two states or between these two states, and the field or the potential energy landscape that the electron feels can change as well. In symbols, when we calculate the two-photon amplitude, we just need to realize that the dipole operator, which represents the second interaction, is not just the dipole operator acting on the photoelectron, but also a one that acts on the residual ion. And as there are two terms, there will be two contributions to the two-photon amplitude. And if we substitute it to the formula for the rabbit delay, this propagates to arising or creation of an extra term in the high energy expansion of the rabbit time delays. How this looks like in some real example is illustrated here again on this carbon dioxide model, which I just mentioned. So what we see here are energy dependencies of time delays for the first four states of the residual cation. And the yellow curves show here in all of these plots the accurate two-photon delay, the quantity that would be measured by a rabbit experiment. The brown curve instead shows the asymptotic expansion of this delay. It shows the sum of the components that really contribute to this rabbit delay in the limit of large energies. If we look at the first two states, X and A, in the top plots, we see that all we need is to sum up the molecular delay, the one-photon delay, and the continuum coupling as was the case before. But to get agreement between the yellow and brown for the B and C states, we really need to include this ion-ion coupling delay, which is also isolated here as the dash dot curve, showing that it has magnitude of around 20 at a second. So it's not negligible. Another topic is the interaction of the molecule with the infrared field in the initial or final state. So we have a polar molecule, and we ask what is the energy of a polar molecule in an infrared field. This is not just the energy of the state itself in a field-free case, but we also need to consider that that the molecule has some permanent dipole, and there is some time-dependent field strength of the infrared field. This also means that the initial state won't be as simple as just exponential of the time and energy, but there will be some additional term in this exponent of the exponential proportional to the vector potential, so that the derivative of this exponent gives us the energy. If we assume that the infrared field has harmonic time dependence, we can expand the exponential using Bessel functions as plain constant coefficient exponentials, and we see that the initial state now becomes a superposition of infinitely many equally spaced states of different energies, and that changes immediately the rabbit picture, because whereas in the standard rabbit we had just these two pathways featuring the two-photon transitions, we now need to consider many more transitions which start from initial state that is shifted from the original field-free initial state by some amount, by some integer multiple of the infrared frequency. Fortunately for us, the high orders of this M do not contribute, and all that needs to be considered at low energies or intensities, or low intensities of the infrared field are these one photon pathways. So the rabbit time delay then becomes much simpler, and what only changes is that the amplitudes that enter the formula are combinations of the 2 photon pathways and 1 photon pathways. The final state, the residual ion state, can also be dressed, and what changes if we include this dressing is again that there are some 1 photon amplitudes entering the formula. So this is the complete picture of the rabbit in a polar molecule, and this can be somehow worked upon in the high energy limit. So we have the formula for the rabbit time delay, and if we put in these combined amplitudes and do some algebra, we find out that the rabbit time delay of the polar molecule will be a combination of the time delay of non-polar molecule and some correcting factor. And this correcting factor actually already has a name. It's a known formula for so-called dipole laser coupling, and it has been derived in the framework or in the field of attosecond streaking, but not in the context of rabbit so far. And this is the interesting new information that rabbit can bring as well. So to give an illustration, I'm showing here time delays for lithium hydride, for ionization of lithium hydride obtained in the rabbit method. The field polarization is along the molecular axis, and the photoelectron leaves either the lithium end in the left picture and or the hydrogen end in the right-hand picture. What is shown here is a comparison between the full time-dependent, non-perturbative, complete rabbit simulation using an attosecond pulse train, which is drawn by the red circles. Then there is the 2 photon or second order perturbation theory, a straightforward one, which contains no dressing, which this is given by the green dashed dot curve. And then there is the corrected second order perturbation theory with addition of the 1 photon pathways. And this is the blue curve. And apparently it gives exactly the needed shift so that these 2 curves agree, the time dependent and the time independent. We also did some simulations of the streaking, and they land on the same curve. So that was the molecular laser dipole interaction. One could ask, is there any delay that comes from molecule photoelectron dipole interaction? I mean, any delay that could be separated and affects the delay in the infrared interaction stage? Well, this is a little bit more technical, and I will not go into details. I will show only the final plot here. So what we see here is a photo detachment of a beryllium hydride minus. This leaves a neutral residual molecule so that there is no continuum delay, no charge acting on the photoelectron, only the dipole. And we compare here the 1 photon delay, Eisenbach-Wigner-Smith in purple, then the complete rabbit calculation with dressing by the IR field, which is given in orange. And then let's say the green one is important, is a combination of Eisenbach-Wigner-Smith delay and the dipole laser coupling, which is green. And we see that these curves asymptotically tend to each other, and then there is no extra term coming from the long-range molecular photoelectron dipole interaction. I will just show this plot and to mention that we are calculating the multi-photon matrix elements or amplitudes by R matrix methods, which separate the difficult problem from which is only in a finite subset of the space from a simple model in the remainder of the space and jump to the conclusions. So Rabbit delays asymptotically, that means for high energies, can be split into many terms, and these terms give us some interesting insight into the molecule. One of them is the ion-ion coupling delay, which is caused by absorption of the IR photon by the residual ion, and it reveals the field-driven dynamics in the coupled two-level subsystem of the residual ion. Then there is dipole laser coupling, which in the context of Rabbit is caused by dressing of the initial or final state by the infrared field. It quantifies some dynamics in the initial and final state of the molecule. And interestingly, we were able to derive the same asymptotic high energy formula for tau DLC as in the streaking. And there is no, it seems that there is no extra asymptotic delay for photoelectron dipole interaction. We use some interesting and useful tools for these calculations. It's the UKRML Plus package, which focuses on electron molecule scattering and multiphoton ionization. And we also used the RMT, R matrix with time dependence, for arbitrary field, non-perturbative time-dependent simulations. That was my talk. I thank you for your attention, and if you have any questions, let me know.
Thank you very much, Jakub, for this very nice and very clear talk. We have time for one or two questions. Please, if you have a question, just ask or raise your hand. Mikhail Yapikin.
Yes. Do you hear me?
Yes.
Yes. You show the picture for oriented molecule, for the poly molecule.
Yes.
And in the picture, the molecule was oriented along the laser polarization vector. What will change if the molecule ensemble will be chaotically oriented?
If the polarization is perpendicular to the molecule and to the emission of the electron, then there is no effect. If the polarization is somewhere in between, there is some effect. But what I wanted to show here was the configuration where the effect is really maximal. And this is for the collinear orientation. If we do orientation averaging, and I did not show this picture, some effect of this dipole laser coupling survives. So in completely general unoriented experiment at low energies, there is still some signature of this dipole laser coupling, but at high energies it disappears for unoriented molecules.
Okay, thank you very much. I see another question from Vasily Streitkov.
Yes, could you please comment on the following? So from the very naive viewpoint, what is the meaning of this new delays? For example, the delays linked with the ion contribution, because naively one would say that when the electron is ionized and it does not know what happens with the ion. And so could you please explain what is wrong in this naive explanation?
In this multi-channel experiment, as you said, we are detecting electron which was created coupled to some specific state, and this state can be then changed by means of the infrared interaction to some other state. And this interaction, or this by means of energy sharing between the ion and the photoelectron, this interaction or this change between the state can pull or push in some sense the photoelectron, which is still nearby. So this is how I perceive this problem. If you know what I mean.
Okay, thank you very much.
Okay, thank you
for answering the question. We have to move on. Thanks for this nice talk. And we move on to Tatiana Sarantseva. She's from the Department of Physics from Voronezh State University in Voronezh, Russia, and the Department of Radio Physics at Lobachevsky State University in Nizhny Novgorod. She's talking about high order harmonic generation in orthogonal infrared and XUV pulses, XUV initiated channel separation and polarization control. Thanks a lot. Tatiana, please go ahead.
Thank you very much for this kind invitation here. And today I want to talk about high order harmonic generation, and especially about XUV-initiated harmonic generation. And this work was done in Voronezh State University, and this collaboration with the group of University of Nizhny Novgorod. And the first of all, I'd like to speak what is I mean by XUV-initiated HEG. And we all know that generally, if you have only IR field in your problem, then HEG can be presented as a three-step process. And the first step is tunneling, the second step is propagation, and the third step is recombination. And if you add additional XUV pulse to the intense IR field, then there is another channel, possible channel when your electron ionized not by tunneling under the barrier, but directly by absorption of high-energy XUV photon. And then it propagates in IR field, and its motion along the closed trajectory is governed by only IR field, and then it can recombinate back and generate some high harmonic. And there was lots of experimental works on this topic, and even on this workshop, we have a very exciting talk by Luis de Mauro about these processes. And the problem here is that we have this XUV-initiated process, and it is very interesting because you have a very high control over high HEG process, because you can control the time when electron ionize, you can control, select only one trajectory here by making the XUV pulse shorter, but you still have your normal IR induced HEG, and the question is how to separate this XUV-initiated channel from the other channels. And the solution which is used now is just to drop the intensity of IR field. And it is really well because the tunneling is very sensitive to the intensity of IR field, and by dropping the intensity, you reduce the IR-initiated HEG. But with this, you have the decreasing of conductive energy, and as a result, the decreasing of the maximum energy of returning electron. And to some degree, you can fix it by going to the higher wavelengths, and it is what I heard from Luis de Mauro, but we're interested in, is there any other ways to separate XUV-initiated HEG without dropping the intensity of IR field and dropping the electron conductive energy? And what other avenues do we have? The first idea we have is that besides the intensity and wavelength of IR field, we also have the mutual orientation of polarization of IR field and XUV field. And the second idea we have is that we can do something to the atomic target and look how its special symmetry affects the HEG process. So we suggested that instead of using collinear geometry of the experiment, we use the orthogonal geometry where the IR pulse and XUV pulse are mutually polarized in orthogonal directions. So you have the E0 is a vector polarization of IR field, and E1 is the vector polarization of XUV field, and the scalar product of these two vectors equal to 0. And we are interested in regime where II field is very strong, so we have the tunneling regime and standard rescattering processes, and XUV field is in the perturbative regime, and so it either should be rather weak, or it even could be, the intensity of XUV field even could be as large as the intensity of IR field, because the frequency of XUV field is high. And if we look at unpolarized spherical symmetric atom, what we can derive from general idea. So if you have only IR field, then your laser-induced dipole momentum can be constructed only from E0 vectors, and as a result, you have it will be directed along this E0 vector. So the harmonic will have the same polarization as IR field. And our XUV initiated process is first order perturbation theory process from this point of view, because we have absorption of only one photon of XUV field. So we have any number of E0 vectors and only one E1 vector. And as a result, the dipole momentum could be orientated only along this E1 vector, because this vector could not be coupling with any other E0 vectors, since its scalar product equal to 0. So what we see that if we look on a high harmonic generation from unpolarized atom in orthogonal geometry, then XUV initiated harmonics should have the same polarization as XUV field. So we come to the idea of polarization filtering. So if you measure harmonics which have a polarization coincides with XUV field, then you measure only XUV initiated HHG and not IR ionization HHG. And based on this simple idea, so we are interested how it may be realized for different system, and we start with the simple system of an atom having an outer p electron. And usually, if we look at the p state, it is 3 times degenerate, and the external field drops this symmetry, and we have 3 independent states. And if we have only IR field, one-dimensional, linearly polarized in some direction, then only one states from this, only one magnetic states from these two, from these 3 states give contribution to high harmonic generation process. And these states have 0 angular momentum projection on the axis coincides with the polarization of IR field. But if you add additional field and the general field becomes 2-dimensional, that to describe high harmonic generation signal, you should take into account not only this state, but also the state which are oriented along the orthogonal direction. And it was investigated in these articles for elliptically polarized field or for general field and its second harmonic. And we thought that for the case if as an additional field we use XUV field, the role of this state also should be important. What theoretical methods do we use? As a basic theoretical background, we choose a diabatic theorem for our dressed atomic wave function, and it was presented in this work. It's rather recent. And according to this work, the wave function of the IR dressed atoms can be presented in the form where we can deduce the slow term. It is just an atomic wave function, and the rescattering term, which describes the rescattering processes in HEG or in any other photo process here. And this rescattering part can be presented as a sum over different closed electron trajectories of the continuum state with outgoing asymptotic on the big distances, where Ks is the instantaneous and the moment of time t electron momentum. And this coefficient Rs, here we are interested in how the symmetry of our initial state implies on this coefficient. And this coefficient includes this form factor, which coincides with the angular part of the initial wave function, and it form factor from this complex vector, and this complex vector is proportional to the polarization vector of IR field. So this form factor will be non-zero only for phi minus state, and for phi plus state, the state that are oriented perpendicular to IR field polarization vector, it is 0. And this is why we have now the only one state give main contribution to IR induced HHG. And based on this wave function, we can construct the perturbation theory. So we can use this wave function as a basic function for the perturbation theory in XUV field. And as a result, what we have an analytical form for the laser-induced dipole. And the general form of this dipole looks like the sum over all closed electron trajectories. And here we have three factors. So the first factor is this one. It's the product of dipole transition elements from the ground state to the continuum state with instantaneous k. And the propagation factor describes the motion of an electron along closed trajectory. And the last factor is electron transition from continuum state to the initially bound state. And what we're interested in is the symmetry of these two factors, of the factor D here in an ionization step and the factor D here on recombination step. And what we can extract from there, we can show that if we can calculate this angular part of this matrix element for the case when the momentum of an electron directed along the polarization of IR field, and this is necessary to electron to return to the core. Then for C minus state, which orientated along the polarization of IR field, this dipole transition element is proportional to E0 vector, and since it multiplies by the E1 vector, the whole ionization factor turns to 0. So we have no XUV-initiated HHG from this state. And the same, if we look at the second state, then this dipole transition matrix element is proportional to E1, and this scalar product is non-zero. So we have XUV-initiated HHG from this state. And if we look at the recombination dipole matrix element, it is also proportional to the E1 vector. It means that the polarization of harmonics, XUV-initiated harmonics, coincides with the polarization of XUV field. So it is what we are expected. And the interesting fact here that we have two separate states, and one state gives contribution to XUV, IR-initiated HHG, and the second state gives contribution to XUV-initiated HHG. And to check our analytical prediction, we make our colleagues in Nizhny Novgorod make TDSE calculation for neon atoms. And here we can see the HHG yield with fixed polarization. On the figure on the panel A, it is with for harmonics polarized along IR field. And the panel B is for harmonics polarized along XUV field or polarization vectors. And what we can see that those harmonics which have the polarization along x-axis and the red line, the red curve is for C minus state, and blue curve is for C plus state. And this dashed black line is just II-initiated HHG without any XUV field. So what we can see that in this case, we have for the harmonics polarized along x-axis, we have clearly only II-initiated HHG. And if we look at harmonics which have the polarization coincide with XUV field, we have here quite different situation. We have different trajectories here. So we can say that here we can see XUV-initiated HHG. And if you can look here, as blue curve is for C plus state, for Y component of the dipole matrix element, it is dominant, and the C minus state is much smaller, give much smaller signal. So to summarize this part of my talk, I'd like to say that the channel separation for orthogonal geometry can be made in two different ways. First, it's polarization filtering, when you measure HHG signal with fixed polarization. And the second variant is if you prepare your atom in some polarized state, then for any intensity, you'll see only XUV-initiated HHG. And very briefly, I'd like to talk about...
Diana, you're basically at the end of your time, so please just mentioning.
Wait a small remarks. So if you have unpolarized atoms, then you have then the change in XUV pulse parameter, you change actually only the Y component of the dipole. So by changing the XUV pulse parameters such as intensity and time delay, you can control harmonics polarization. And on this slide, you can see that for how the polarization of harmonics different for different time delays. So by changing the time delay, you can control the polarization of your harmonics if you use unpolarized atom as a target. So thank you for your attention and sorry for being out of the time.
It's okay. Thank you very much, Tatiana. Thank you. We can have one question. Is there one urgent question from the audience? Please raise your hand or just speak up. I don't see anybody. I have a question. Could you go back to the slide where you showed the harmonic yield, like one back here? What is the blue bump in panel A?
What? This blue pump is a second harmonic of XUV field, and actually the next talk, or the talk after the next, will be about this bump in more detail.
All right. Thank you very much for answering the question. And we move on to the next speaker, Alexander Flegel, also from Voronezh State University and Lobachevsky State University in Nizhny Novgorod. He's going to talk about XUV rectification effect in the IR dress medium. Please go ahead. Now we see the slide, but I cannot hear you.
Okay, now?
Now we can hear. I can hear you. Yeah, sorry. Okay. Maybe you start again.
Okay. This work is done with collaboration with Misha Frolov. Sorry, just some technical problems. I will start with some history. The rectification effect is a well-known effect, and it has been measured for first time more than 60 years ago. And here you can see the first photographs of the response of the crystal on the laser field. Here you can see some constant reaction, which illustrate the almost constant polarization of the crystal when the laser field goes through it. This is references to the first papers. And rectification effect consists in inducing of the quasi-static dipole moment in a target system interacting with intense low frequency field. It's interesting and important that this effect is unobservable in an optically transparent medium with central symmetry, so that only non-dipole corrections can be used to explain this effect in atoms. In this reason, this effect was kind of repulsive for researchers who work with atoms. In this work, we asked the question if it's possible to induce quasi-static dipole moment in single atom, which interacts with superposition of two pulses. One of them is extreme ultraviolet pulse, and the second one is infrared pulse. And we want to rectify this highly oscillating pulse. The answer on this question is yes. And first of all, I would like to explain qualitatively the physical mechanism of this effect. So if we consider these two pulses, we will assume, it's a very important assumption, that the duration of the XUV pulse is much less than the cycle of the infrared pulse. And of course, there's some kind of time delay, and time delay is defined by this formula. Okay, and on the time scale of the XUV pulse, the atom becomes polarized due to photon exchange. So initially, the atom is in the IR-dressed field, but this IR dressing can be replaced by DC dressing because duration of the XUV pulse is very short, and we can describe the infrared pulse, infrared field as a static or DC field evaluated at the time delay. And the initial state propagator and the final state, it's DC addressed states. And of course, such polarization will depend non-linearly on the DC field. In this case, if it's so, but it's so, we have some stark shift of the bound level of the optically active electron. And this stark shift will depend on the DC field somehow non-linearly. And in accordance with Hellman-Feynman theorem, this very known approach, in order to evaluate the dipole moment, we should evaluate the derivative of the energy with respect to the field. So I emphasize that this formula is very qualitative, but I will show on the next slides that this result is very close, very similar to the exact results which we obtained from quantum mechanical approach. As just in the previous talk, Tanya said, we use combination of adiabatic approximation in order to describe interaction with the infrared pulse and non-stationary perturbation theory to describe the interaction with the XUV pulse. And combining these two approaches allows us to describe the response of an atom to both of these fields. And omitting all derivation details, I will show the final result, which is here. This is quasi-static dipole moment. We can see that only two factors depends on time here. The first factor is square root of the envelope of XUV pulse. And the second one is the polarization of the atom, of IR-dressed atom. And I should mention here that we just don't use exact value of the polarization, which is defined below, but we use analytic part of this polarizability with respect to the field, because it's known that in the static field, such matrix elements contains some kind of oscillations. You can see here the positive energy. When electron absorbs the XUV photon, its energy becomes positive, and we have, in fact, two classical trajectories for this electron. One towards the barrier composed from DC field, and another one from this barrier. And these two trajectories, after reflection of electron, can interfere, and such kind of oscillations here of this from this interference gives some unphysical features. It's a result of approximation. It's not follows from exact theory. So after such averaging of this polarizability, we obtain a new polarizability, overline polarizability with analytic function, which is analytic function of field. And in the case of weak fields or moderate fields, because we use atomic units, it means this condition means that the field is less than atomic field. Such polarizability can be approximated by a linear term, and beta is just fourth order susceptibility or hyperpolarizability of the DC-ferrite atom. After averaging over time, this dipole moment gives us the average quasi-static dipole moment, which differs from the qualitative result only by this pulse shape factor, which we calculated it, and which this factor is for most of pulses just simple to unity. For small fields, again, we have very simple formula, and this formula explains, in fact, the rectification of XUV radiation by single atom. For energies of XUV photon larger than ionization potential, this vector is complex, and imaginary part of this vector indicates the total current and near zero frequencies, and the real part just polarization of an atomic target. In order to illustrate this effect, we used very simple model, which is delta potential model or zero range potential model. Of course, it doesn't reflect all features of atom, but gives the general features of the rectification. I won't read all these parameters which we used. We can return to them. But what is nice for this potential, that polarizability is known. We just took it from this paper. And here is numerical results. First, I would like to show the dependence of average quasi-static dipole moment as a function of time delay. And we can see that this profile of such dipole moment perfectly replicates the profile of infrared pulse. Different colors corresponds to different intensities. And for small intensities, we have good agreement, but for larger intensities, some disagreement near the local maxima of the field. And this disagreement is related with nonlinear effects in atomic polarizability. To clarify these effects, we introduce two factors, which are in fact ratio of the derivative of polarizability to the field-independent parameter beta. For field equals to 0, we have unit, and then some disagreement from this linear unit, from unit, which means linear dependence. And I would say that up to 0.11 petawatt per centimeter squared, we have almost linear dependence of the rectification effect on the infrared field. And here on this slide, we show time evolution of the rectification effect as a function of time delays. So for different time delays, we can see how response of the atom depends on the time. The color shows the magnitude of the real part of the quasi-static dipole moment. We see that profile of this dipole moment is almost replicated by, or replicates the squared envelope of the XEV pulse. The magnitude is proportional to the magnitude of infrared pulse. Pink line here is infrared pulse. And this profile is almost symmetrical, except of some tiny region around the zero of infrared pulse, of infrared field. And also what I want to say, I return back to the slide, that this rectification effect, I mean, the dipole moment, is very nice controllable by the direction of the infrared field. Let me now summarize my work. First, the XEV rectification effect can be observable for infrared-based atomic media, for example, for atomic gas. So we can say about atom like about atomic rectifier for extremely highly oscillating XEV pulse. The quasi-static dipole moment is induced by the time scale of attosecond XEV pulse. So it's very ultra-fast response. And the direction of DFT is determined by the opposite direction of the infrared field. These two items allows us to expect that this effect can be used for ultra-fast optical gating. Thank you for your attention.
Thank you very much for your nice talk. Other questions from the audience? I actually see no question. Could you please go back to, I think it was slide 10. It was only very short time on the, yeah, no, this one, 8. I didn't get exactly, if you look at, no, 8, sorry, number 8.
This is number 8. 8, sorry.
This is, yeah. Actually, I did not, maybe was not fast enough in following. Why is, if you look at the red line in the upper panel, I see kind of a cut in the two negative peaks and really a kind of inversion in the positive peak. Do you see what I mean?
Yes.
Yeah. Where does it come from?
No, it's hard to say why we have such kind of difference, because, for example, for imaginary part, we have absolutely different. We have increments here. Here we have decrement.
Yes.
But if we return back to the polarizability, which is in fact the important parameter here, I would say here, this polarizability, it non-linearly depends on the infrared field. This field is instantaneous value of the infrared field. And only for small fields, for weak fields, we have such kind of linear dependence. For larger intensities, this is broken, and we should take into account nonlinear effects. And this nonlinear effects only means which sign has the second term of expansion over field. Here this term is negative, here this term is positive, and in order to analyze it, we should analyze atomic susceptibilities of higher orders. You see, it's a very difficult question to answer why we have such kind of nonlinearity or another kind of linearity. And of course, it depends on the model. For different atoms, it will be different. We used only simple delta potential model, zero range potential model. So.
Okay, yeah, thank you. I see a question by Vladimir Antonov.
Thank you, Alexander, for this nice talk. And my question is about the optical gating. You mentioned that this rectification can be used for some ultra-fast gating. Could you explain it in a few words?
Okay. First of all, this picture, it shows that atomic response or rectification polarization replicates the infrared pulse. It's first one. Then on which duration we obtain such response. If you look at this picture, we see that durations, so here time, the duration of such polarization is the same as duration of XUV pulse. If we have XUV pulse of attoseconds, then each duration of pulse during this XUV pulse, we will obtain such kind of polarization. So we obtain polarization, and this polarization depends on the direction of an infrared pulse and replicates the infrared pulse. So we can obtain the profile of infrared pulse measuring the polarization of the target of the atom. So what I mean.
How we can measure the polarization?
Yeah, we can measure polarization. How we can measure? For example, we can measure not polarization. We can measure current near zero frequencies.
But would not it be the frequency of the other field? I mean, I guess intuitively that this effect will result just in reshaping of the other pulse at the output from the medium. Am I right?
I think that, for example, here parameters which we used for calculation, for illustration, but in fact, infrared pulse doesn't matter which frequency of infrared pulse. It's just what we need is tunneling regime. So any infrared pulse. About XUV pulse, we used this energy, 60 eV, but it also doesn't matter in fact. So only it should be perturbation regime. So
can we again give a comment?
Broad range of parameters.
Sorry, can I give a comment?
Okay.
The Volodya asks about the frequency of the response, but I think that this frequency corresponds to the time derivative of the envelope of the XUV pulse. And in this figure, we see
time dependence of response is absolutely the same as the envelope of XUV pulse.
It can be higher than the frequency of the infrared field.
I see. Thank you.
It may be, of course, but yeah, it shouldn't be very short, of course. Yes.
Thank you for the explanation.
All right, thanks a lot for this nice discussion. I thank Alexander Flegel once again for answering the questions, and we move on to Alexander Silaev, who already is on the picture. He is affiliated also with Lobachevsky State University and with the Institute of Applied Physics of the Russian Academy of Sciences in Nizhny Novgorod. And he's going to talk about channel separation of secondary generated radiation. in atomic gas is irradiated by orthogonal XUV and infrared pulses. So I guess it's related a bit to schemes we have seen already today. And please go ahead.
Okay, thank you. So in this talk, I will continue the series of talks about the response of atomic systems in the infrared and XUV pulses. So indeed, the addition of the XUV pulse to the intense infrared field gives the new physics, and this gives the new channels of generation of the secondary generated radiation. And I think that the studies of this physics is the beginning of this at this moment. And this work was done in collaboration of the Alexander Romanov and Nikolai Vedensky from Nizhny Novgorod, and Tatiana Sarantseva, Alexander Flegel, and Mikhail Frolov from the Voronezh State University. If we consider the interaction of the atomic target with purely single color infrared field, there is the high-order harmonic generation, which is due to the tunneling of the electron, the propagation of the electron in the continuum, and acceleration and the recombination when the electron approaches the ion. And but in the presence of the XUV pulse, there are additional channels of generation. The first one, which we call XUV assisted recombination channel, consists in the absorption of one XUV photon at the time moment when the electron recombines with the target. And this XUV assisted recombination gives an additional plateau in the high-order harmonic generation spectrum, which comes after the main plateau, and the width of this additional plateau is equal to the frequency of the XUV pulse. And the intensity of this additional plateau is linear with the intensity of the XUV pulse. And also it is determined by the two-photon recombination amplitude cross-section, which is corresponds to the absorption of the XUV photon and the emission of the photon of the higher frequency. And also there are another in several our papers we have shown that this phenomenon can be used for various applications, this additional plateau. For example, it can be used to measure the two-photon cross sections, which corresponds to this phenomenon. Second, this phenomenon of this the appearance of this additional plateau can be used to measure the attosecond XUV pulses, because if we measure the intensity of particular harmonic on this additional plateau as function of the time delay between the infrared field and the XUV pulse, this time dependence can be used to retrieve the waveform of the XUV pulses, which have been shown in our papers. And finally, this time delay dependence of the harmonics on the additional plateau can be used to retrieve the spectrogram of the dipole acceleration induced by the infrared field. So when one can provide the trajectory analysis in the experiment by using the probe XUV pulse. I would like to stop on this third step in more details. Namely, in these figures, you can see the retrieval of the spectrogram of the dipole acceleration induced by the intense infrared field. In the bottom figure, you can see the spectrogram of the dipole acceleration induced by the purely infrared field in the neon atoms, which was calculated numerically by solving the time-dependent Kohn-Sham equations. for the neon atoms. And the top figure is the retrieved spectrogram. And we have retrieved it in the following way. We add the XV pulse, which has the 200 at a second duration, to the infrared field. This addition creates the additional plateau in the harmonic generation spectrum. And here is the dependence of the harmonics on the additional plateau, dependence of the spectra, as a function of the time delay between the XUV pulse and the fundamental field. And it is seen that the map shown here reproduces the spectrogram induced by the infrared field. However, there are some strange spots indicated here with the frequencies of which corresponds to the second, to the doubled frequency of the XV pulse. Note that the frequency scale here is shifted by the frequency of the XV pulse. And these spots interfere with the main signal, which comes from the XV-assisted photo recombination. And these are not the numerical artifacts. These spots come from the XV second harmonic generation. So in the case when the XV pulse interacts with the atom in the presence of the intense infrared field, the symmetry of the system is broken and the second harmonic of the infrared field can be generated. And so these spots interfere with the main signal, and in order to retrieve the clear spectrogram, one should separate the channel, the XV-assisted photo recombination channel, from this second harmonic generation of the XV pulse. However, the phenomenon of the second harmonic generation of the XV pulse is also very useful, and as was shown in our recent paper published in the Physical Review, it can be used to retrieve the waveform of the infrared field as an alternative to the well-known strict camera method to the measurement of the second pulses. And this is similar to the response of the rectifications that was discussed in the previous talk. So both the rectification and the second harmonic of the XV pulse can be used to measure the waveform of the infrared field. And this is due to the fact that the second harmonic intensity of this XV pulse is dependent on the value of the infrared field at which the XV pulse comes at the time moment when the XV pulse arrives to the minimum. And here is the results of the comparison, the numerical calculations of the second harmonic generation intensity for different time delays between XV pulse and infrared field. And we can see that the squared value of the infrared field coincides with the time delay dependence of the second harmonic generation. And this is the analog of the well-known method to measure terahertz radiation using the second harmonic generation due to cubic response of bound electrons in the field of the probe, intense probe infrared field. So we propose the analog of this method, but for the higher frequency range, we propose to measure the optical or infrared pulses by using the short XUV pulses. However, the problem is that in this case, one should measure the second harmonic of the intense XV pulse, and in this case, the frequency of the XV pulse of the doubled frequency of the XV pulse should be higher than the cutoff of the main plateau. But here can be the signal that comes from the XUV-assisted photo recombination channel that I have already mentioned. And this signal can interfere with the second harmonic and give some artifacts. For example, here is the example of the time delay dependence of the signal, which is slightly shift from the second harmonic, with the exact second harmonic. And it is seen that in this case, there are the disagreement with the squared value of the infrared field in the measured signal. And in order to eliminate these differences, one should use the separation of the channels, of the generation channels. The XUV second harmonic generation and XUV assisted photo recombination channel. And in this work that was published in the Optics Letters recently, we proposed the way to separate these channels by using the orthogonal polarizations of the infrared field and the XUV pulse. As was shown by the analytical theory presented by our colleagues from Voronezh, the second harmonic generation of the XUV pulse is polarized along the infrared field direction, while the XUV-assisted photo recombination channel gives the radiation which is polarized along the XUV field. And thus, this can be used to separate the channels. And here is the modeling of this idea. So in order to test this idea, we used the numerical calculations for the argon atom, which interacts with the two-color field, which is the infrared field, and XUV pulse, which are polarized in different directions. And so in order to calculate the response, we use the solution of the 3D time-dependent Schrödinger equation for different orbitals from the outer 3p subshell of the argon atom. In this subshell, there are 6 electrons with different magnetic quantum number and with different spin projections. And so we solve the time-dependent Schrödinger equation with different initial states that correspond to different magnetic quantum number, and then sum the take the sum of dipole accelerations from different orbitals and calculate the full atomic acceleration. And the parameters of the calculations are shown here. Here is the wavelength of the infrared field, which is 1.4 microns, 20 femtosecond duration. The XUV pulse has the frequency 40 electron volts, the duration of 400 attosecond, and we use the equal intensities of the infrared and XUV pulse that corresponds to not so high ionization of the atomic system. And here is the comparison. Here is the example of calculation of the spectra of the dipole acceleration oriented along the x direction, which coincides with the direction of the infrared field, and on the y direction, which coincides with the polarization of the XUV field. We can see that in the x direction, the radiation contains the main plateau, which is due to the high order harmonic generation by the infrared field, and peak at the second harmonic of the XUV pulse, in agreement with the analytical predictions. At the same time, the orthogonal component of the dipole acceleration contains the strong signal on the first harmonic of the XUV pulse, which is the linear response. the third harmonic of the XUV pulse, which comes from the 4-wave mixing in the XUV range. And also here is the XUV assisted channel, which gives the plateau, and therefore, in agreement with the analytical predictions, the XUV assisted recombination channel has the polarization that coincides with the direction of the XUV field. And the second harmonic of the XUV pulse is polarized in the orthogonal direction, and so we obtain the channel separation. This figure, the figure A, shows the time delay dependence of the radiation near the second harmonic as function of the time delay. In the case when the pulses are polarized in orthogonal directions. One can see that in this case, the agreement with the squared infrared field is almost perfect. And in comparison with the case when the pulses are polarized linearly and when there is the contribution from the XUV assisted channel that gives the some disagreement. Also, finally, we have tested the intensity range in which the second harmonic intensity is linear with intensity of the infrared field. So this is the intensity range in which the retrieving of the infrared field waveform can be performed. And we see that there is the upper limit corresponds to the 2 times 10 to 14 watts per centimeter squared, which is the threshold of the system. To summarize, we have proposed the way to separate the channels of the radiation, of the secondary generated radiation due to the second harmonic generation of the XUV pulse and the XUV assisted high order harmonic generation. And this can be done using the orthogonal polarizations of the pulses. And using this orthogonal geometry, one can use separately the XUV assisted photo recombination channel, for example, for retrieving the spectrogram of the dipole acceleration used by the infrared field, or to retrieve the infrared field waveform by measuring the second harmonic of the XUV pulse. That's all. Thank you for your attention.
Thank you very much for your nice talk and your interesting results. Can you comment on the kind of efficiency of the second harmonic generation? So I have seen
efficiency.
You showed this nice harmonic spectrum where then the second harmonic of the 40 electron volts showed up at 80 electron volts. Maybe the previous, yeah, this one. What is the
here is. The efficiency depends on the target. Second, it depends on the frequency of the XUV field. For example, the last second harmonic intensity for different XUV field frequencies. And one can see that for 60 electron volts, the intensity is higher than 1. So it decreases with increasing the frequency of the XUV field. But currently we are in the process of this study of this efficiency of this radiation, because in order to accurately determine the efficiency, one should use multi-electron calculations, because also the multi-electron effects can influence this efficiency. So we are currently in the process.
All right, thank you. I see a question by Barry Walker.
Hi, thank you. A very nice talk, but I think mine would be a follow-up question, actually just an add-on, because a lot of the graphs and the results are in arbitrary units. And so I wondered what was the motivation for that? Is there some way that this could be put into atomic units for a particular system, or even like, rates per second? Because a yield is typically spatially and temporally integrated, right? And I think a lot of these are rates instead. I don't know. It's confusing to me. You understand? Like, as there's a difference between a rate per second and a spatially temporally integrated yield. So these are just temporally integrated yields. So I guess my question is, or my comment is on the units, and also arbitrary versus like absolutes, and if there's a way to gauge this. So it's kind of a follow-up question, because that's what it is. Yeah.
Okay, thank you for the question. We give the arbitrary units and the figures because of two reasons. Because the first is that sometimes we provide the comparison with the analytical calculations, and there are not the theory up to some constant value, and so it is better to comparison with the arbitrary units. The first reason is that sometimes we provide the dependencies of some yield, which can be the intensity of the radiation or the integrated intensity, which is the energy, for example, energy of the harmonic. But they also differs by some constant factor, and so it is better to use the arbitrary units because they are these dependents are the same.
Okay, thank you. It's just hard to, like, as an experimentalist, it's hard for me to like transfer this into a system without that like additional specificity, and for me to fully appreciate the impact of the results or applicability. So that was common. But thank you for clarifying.
But currently we are in the process of determine the absolute values of the efficiencies of the generation of the, for example, generation of the second harmonic, and so then we provide the values in the absolute units.
Right, thank you very much. There is another question by Vladimir Antonov.
Sasha, thank you very much for this interesting talk. And my question is about the propagation effects. Don't you want in the future to consider macroscopic propagation? Since when you speak about efficiency, it is, as I understand, this is just a single particle response. But in the experiment, you deal with the propagation, and in this case, how large could be the efficiency of second harmonic generation, and what effects could limit it? What do you think?
I think that the limiting factor is the phase matching, of course, between the generated radiation and the infrared pulse, because we use some the high intensities of the infrared field in order to obtain strong second harmonic, for example. And so the gas ionization by these strong intensities can lead to the phase mismatching. But in this result, the presented results, we are aimed to for retrieving, not to generate the high efficiency the radiation, but to use it to retrieve, for example, to retrieve the waveform of the infrared field, and therefore by making the pressure of the gas very small, we can eliminate some effects that, for example, we can eliminate the phase mismatching, and so therefore in this talk we did not describe. We have neglected this effects, but maybe in future we will consider it.
Thank you, Sasha. You answered the question.
All right. Okay. One last question by Michael Ryapikin.
Sasha, could you please show the slide with with spectrograms you showed? Yes. When I look at these two figures, I do not see any significant difference. In both cases, the skeleton of these spectrograms is well defined, and if I were an experimentalist, I could simply ignore these weak modulations. Why
Thank you for the question.
So important to separate the contribution due to second harmonic generation?
Because if we take higher intensity of the XV pulse, which is quadratic in the intensity, the second harmonic intensity is quadratic in the XV pulse intensity, and therefore these spots will be more pronounced. And also, if you see on this curve, which is the first curve, which corresponds to the small times, here is the disagreement. So in the large disagreement, and this is due to the fact that the second harmonic generation interferes with the signal on this short trajectory, which is given by the XV-assisted photo recombination. So,
Sasha, nevertheless, the skeleton is quite the same.
The skeleton is the same.
Which is most important. The skeleton is most important in this case.
But if one needs some more details, it can matter.
Yeah. All right. Yeah. Thanks for answering all these questions. Let's thank Alexander and all the other speakers of the session. And it was a very interesting session. I hope I will see you in the plenary session in half an hour. And thanks for participating. Bye-bye.
Goodbye. Thank you.
Goodbye.